Welcome back my dear friends. A very good morning, good afternoon, good evening to all of you. And as you know, this is the DADM 3, which is Data Analysis and Decision Making 3 course under NPTEL MOOC series, which is 30 contact hours, which when broken down into number of lectures is 60, because each lecture is for half an hour. And we have, if you can see the slide, it is the 9th week going on. So, you have already completed 8 weeks, each week with 5 lectures of half an hour each, and if you have already taken such 8 assignments. After the 9th one, you will have the 9th and so on and so forth till the 12th one, and after the end of this course, you will have the final examination. My good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, if you remember, we are discussing about general formulation of integer programming, and I am again reiterating that the concept of trying to formulate the problem in the right perspective with the decision variables, objective functions, constraint is the main idea in operation research, but we are more discussing in this course about the methodology of solution. So, I will try to basically highlight few of the points for modeling, which will also give you some idea that how innovative the modelings can be. In the last example which we did in the 41st lecture was basically trying to plan the location of the fire brigade, considering there are 6 cities in a district in any part in India, and there is some minimum time or maximum time which the fire brigade engines can take to reach from city 1 to city 2 or so on and so forth, and based on that we found out that where the fire engines would be built up. At the fag end of the 41st lecture, we started the discussion about Indian Auto Company, and is basically going to manufacture 3 different types of automobiles or cars, and we did not finish it. So, I will again restart the examination of that problem, such that you will understand the nitty-gritties and the innovativeness of how the overall methodology of formulation is done, while the methodology of solution is already discussed, which is basically the Gomori cut and the branch and bound. I will come to the branch and bound later. So, the problem is again like this, you have already seen it, but I will still repeat. So, please bear with me. Indian Auto is considering manufacturing 3 types of autos or cars, which are the compact, the mid size and the large one, depending on the seating capacity, the mileage, so on and so forth. The resources required for and the profits yielded by each car are shown in the table, which we will follow. Currently, in the next slide, currently 9,000 tons of steel and 60,000 hours of labours are available. So, that requirement of steel, requirement of labor can be per unit time. So, that unit time can be either a week or a month or a quarter or whatever it is. For production of a type of car to be economically feasible, at least 1000 cars of that type must be produced. So, if you are producing compact or mid size or large, you have to produce 1000 or more in order to be profitable, because for manufacturing each car there is a cost plus there is a selling price. So, over and above 1000 and above would definitely make it into a reality that there is some profit. We need to basically formulate an integer programming problem, and in order to maximize Indian Auto's profit. So, here the overall idea that what should be the objective function has already been stated, is basically a maximization problem, and we need to basically find the overall profit for the same. So, as I just mentioned when we were reading the last slide, the details about the compact, mid size and large, the steel requirement, the labor requirement and the profit yielded in rupees would be basically discussed, and here are the figures on the data. So, in the first column you have the steel requirement in tons, labor requirement in hours and profit yielded in rupees, and on the topmost row you have the car type, which is compact, mid size and large. The corresponding values for steel requirement, I will read the values. It is 1.5, obviously the units are already given in the first column. So, I am not going to repeat it. It is 1.5, 3 and 5 for compact, mid size and large. The corresponding values for these type of cars for the labor requirement is 30, 25, 40, and the profit which comes out, that means the selling price minus the cost price means all the cost component included which is subtracted from the revenues is basically for the each car for the variety of compact, mid size and large are respectively like these values 2000, 3000 and 4000. So, because Indian Auto must determine how many cars of each type should be built, so we define these numbers as follows: x suffix 1. So, the 1, 2, 3 whatever I mentioned I have already told time and again they are basically the suffixes and depending on the problem formulation. So, you have x 1, x 2 and x 3 which denotes the number of compact cars being produced, number of mid size cars being produced and number of large cars being produced. So, obviously, if the profits are 2000, 3000 and 4000 and your main aim considering the profit maximization is the main idea of this problem, the integer programming objective function would be 2 x 1 plus 3 x 2 plus 4 x 3 has to be maximized, and we need to find out those values of x 1, x 2, x 3 based on some constraints which will basically be restricted considering the number of labor hours you have, considering the number of tonnage of steel which you can utilize. And also remember that there is a minimum capacity build up which has to be done for each and every car of the 3 variety in order to basically bring profitability into the picture. So, hence we need to maximize 2 x 1, I am just repeating it, 2 x 1 plus 3 x 2 plus 4 x 3. Now, what are the constraints that will come in the next slide. So, we already know and we have read it very clearly that if any car of a given type is produced, then at least 1000 number of that car type should be produced in order to basically make a profit. So, in that case we know that x 1, x 2, x 3 are the decision variables corresponding to the type of cars which are being produced. So, in that case x 1 should be greater than 1000, and in case if x 1 is 0. So, obviously, that means it would not have any car produced. So, it can be 0 or some values over 1000 like 1000, 1001, 1002 so on and so forth. So, any number in between is not allowed because that would not bring profitability into the picture for the type of car which you are producing. So, the constraints are x 1, x 2, x 3 are less than equal to 0. So, obviously, they cannot be negative, but their values would be 0, and in other sense their values of x 1, x 2, x 3 are greater than equal to 1000. That is the first 3 constraints corresponding to the car 1, car 2, car 3 type. The fourth and the fifth constraints are related to the tonnage of steel being utilized and the number of labor hours being utilized. So, constraint 4 would be the car produced can use at most 6000 tons of steel and the cars produced can use at most 60,000 hours of labor. So, these would also be brought into the picture as the constraints. So, let us define that we will define the functions accordingly in order to make an innovative formulation. So, what we will do is that we will replace the constraint 1 by the following pairs of constraint which is like this. We will define a new set of decision variables y 1, y 2, y 3 and they would be done accordingly. So, we will basically find out that x 1 is less than equal to m 1 into y 1. Hence, the first constraint would be done in such a way, because what we are trying to do is that if you remember the x values were either 0 or they were 1000, 1001, 1002 so on and so forth. So, there was a gap or a discreteness, but what we will try to do is that we will try to formulate the problem in such a way that rather than having x we will basically bring y. So, y would now be a problem formulation of the 0 1 type. So, any production of 0 or 1000 and above would give the value of y as say for example 1, and any other value which is not feasible for profitability to be true, in that case y can be 0. So, it can be other way around also, that for no profitability y 1 can be or y's can be 1 and for profitability it can be 0, but we will basically formulate it as for profitability we have y's as 1 and non profitability we will have y's as 0. So, this is how we formulate. So, if you remember we had 1000 as the minimum number. So, if I look at the equation, I will highlight it. If we look at this equation, so consider 1000 minus x 1. So, any values below the value of 1000 obviously would not be profitable. So, in that case if y is 1, so in that case m 1 is 0. So, you will basically have m 1 into 0 is greater than 1000 minus x 1, which would basically violate or not violate depending on the equations values of y 1 is equal to 0 and 1 we have. So, any value of y is equal to 0 or 1 would basically be satisfied by this equation, because now we are changing the decision variables from x 1 to y 1, x 2 to y 2, x 3 to y 3 like this. 1000 minus x 1 is less than equal to m 1 into 1 minus y 1. So, if y 1 is 0 or y 1 is 1, you will basically have the values of x 1 defined accordingly. Now, let us read it further. To ensure that both x 1 and 1000 minus x 1 will never exceed m 1. M 1 is basically a maximum value of which we are trying to put for the values of x 1 or 1000 minus x 1. It is sufficient to choose m 1 as large as possible, such that m 1 exceeds 1000 and x 1 is, and these values of x 1 would always be less than m 1. So, if say for example, we have the concept that we want to build say for example 2000 compacts, if in case we wanting to build. So, it will be basically would be available depending on the number of labor hours, because the reason being you have 6000 1000 to be produced. So, you need labor hours. So, if you basically multiply the labor hours for compact, it will be 30 into number of cars which is produced is 1000. So, the total number of labor hours utilized would be 30 into 1000 will be 30,000. Now, having said that, we should pause. The reason is we have already mentioned that the cars produced can use at most 60,000 hours of labor. So, depending on the combined one or the single one utilization of labor hours, it should never basically exceed 60,000. Similarly, would be the case of tonnage of steel which is being utilized. So, building 60,000, which is the total number of labor hours, divided by 30, which is the number of hours required to produce that compact one, you will basically have 2000 compacts would use all the available labor. So, it basically eats up. So, in that case, if compact eats up all the labor hours, number of hours, so hence the number of labor hours available for the other two variety would be 0, or other two variety of the cars. But having said that, if you basically utilize the total number of labor hours and which means that you are trying to utilize the steel, but still steel would be left, because only you have eaten up the total number of labor hours, not the total quantum of steel which is there. So, this is what it states. I will read it again. Building 60,000 divided by 30 is equal to 2000 compacts would use all the available labor hours, but it will still leave us with some steel. So, at most 2000 compacts can be built, not more than that, because it is violating one of those constraints. So, you have to basically check that which of the other constraints corresponding to the labor hours required or corresponding to the number of steel requirement utilized is being violated by the first time, and obviously, if one is violated, you have to basically stop there. So, at most 2000 compacts can be built, thus we can choose M 1 as 2000, which means that the values of x 1 cannot exceed 2000, it can be any value starting from 1000 to 2000. So, in this we will try to basically find out the limits for x 2 and x 3 also. Similarly, let us go to constraint 2. Constraint 2 can now also be replaced by the same concept, because if you remember, we have said that we have to produce 1000 number of cars in each FD segment in order to bring profitability. So, the second constraint would be trying to consider that we are trying to bring y 2 into the as the decision variable in place of x 2, such that y 2 is 0 and 1. So, the actual equation becomes 1000 minus x 2 is less than equal to M2 in the bracket 1 minus Y2, where Y2 can be 0 and 1. So, verifying that, we can basically again verify that the total amount of M2 can be 2000. So, here the violation would basically you have to check both the labor hours requirement and the steel hours requirement, required total values. Based on that, you will say that your requirement for the second type of car is basically again 2000. Now, let us go to the third constraint. Third constraint is corresponding to the third variety of car. So, that it becomes again 1000 have to be minimum produced. So, 1000 minus x 3 is less than equal to m 3 in the bracket 1 minus y 3, where y 3 can be the 0 1 variable. The moment you basically consider the constraints one at a time, which is violated the first, based on that you find out that m 3, that is the maximum number of cars which can be produced in the highest category, in the third category would be 1200. So, 2000 for type 1 car, 2000 for type 2 car and 1200 for type 3 car, depending on the violation of which of the constraints is important. So, if you remember, you have to check the violations as you have done it for the first case. So, checking 2000 compact cars will still leave you some steel. Then you will check again number of labor hours and the steel requirement, which is violated first. Based on that, you will say that yes, M 2 can be 2000. Then coming to constraint 3, you will again check labor hours violation. Violation means that constraint is not being met, and the amount of steel requirement, based on that which is violated or that constraint is not met. Based on that, we find out that maximum value of the type 3 car is 1200. Constraint 4, which was constraint 4 and constraint 5, which was related to the number of labor hours and the number of quantum of steel which was being utilized. So, constraint 4 is a straightforward resource constraint, because if you remember, now where does this these values of 1.5, 3 and 5 come. So, let me go back to the slide, the table. So, the table says that compact car, one car being produced will require 1.5 tons, mid size will require 3 tons and large will require 5 tons. So, if you are producing x 1, x 2, x 3, the requirement would be y 1.5 into x 1 plus 3 into x 2 plus 5 into x 3, and what is the total amount of tonnage of steel which is there, that is 60,000. So, we will put the constraints accordingly, and this is how the constraint looks like. 1.5 x 1 plus 3 x 2 plus 5 x 3 is less than equal to 6000 steel constraints which is there. Now, let us come to the last constraint. What is that last constraint? That is related to the labor hour requirement. We have already said that the total number of labor hours requirement is 60,000 number of hours. So, let us check that what is the number of hours required for producing each and every variety of the car. So, that is 30 number of hours for the first type. I am not going back to this the table which you have already seen it number of times. So, it is 30 number of hours for the type 1, 25 number of hours for the type 2 car and 40 number of hours for the type 3. So, obviously, the total number of labor requirement would be 30 x 1 plus 25 x 2 plus 40 x 3, and that should be less than equal to 60,000 number of labor hours, which is the maximum which is available for you. So, I should basically utilize a different color. So, this is labor constraint and this is steel's constraint. So, you have basically converted the labor constraint and steel constraint corresponding to the decision variables. Now, after noting that the problem x 1 is greater than 0 and x 1 must be integer, we obtain the following integer programming, which was maximizing 2 x 1 plus 3 x 2 plus 4 x 3 is what we want to maximize, because you remember 2000 was the profit for selling one car of type 1 compact one. Similarly, 3000 in Indian rupees and 4000 in Indian rupees for the third variety. And the corresponding values, when you find out, when you put the constraints are like this. You have y1, y2, y3 as 0 and 1 depending on whether you exceed or not exceed. And the constraints which have been included, I will start from the last part. So, this one is the constraint due to labor hours. So, it cannot exceed 60,000. This is the number of hours which is required for the number of tonnage of steel utilized. So, the green marked one, light green one is basically corresponding to the x3 quantum. So, if you look at these values, so on the left hand side, that is 1000 is the maximum minimum requirement of cars you have to produce. So, it will be corresponding to x3 or x2 or x1, and here are the data. This is for the second one. Let me check, these are very dark. So, I will try to utilize this. So, this is for the first one, based on that we solve the problem. So, this is the integer linear programming, and also with 0 1 programming, you solve it using any of the methods and you get the answer. So, here remember x1, x2, x3 are greater than 0, and similarly you have brought the decision variable y's, which is 0 and 1 depending on whether you proceed or not proceed. Once you solve the problem, the optimum solution to the IP is you get a profit of 6,000 and the corresponding values of x1, x2, x3 are like this. x1 and x3 are 0 and x2 is 2000. So, which will mean that in that case y2, which is corresponding to the 0 1 variable for the second decision variable, which is x2, is 1, because you are producing cars there, while y1, y3 would be 0, because corresponding values of x1 and x3 are 0. That means, no cars are being produced of the type 1 and a type 3. So, let us double check. So, if it is x2 is 2000, so what is the profit which we had from each and every car which is being produced for type 2 quality? We have seen it was 3000 here into Indian rupees. I am not going to highlight it, I am hovering my pen here. So, 3000 into the number of cars which are being produced will give you the profit, which is 2000 number of cars. So, you will basically have the profit accordingly. So, that will be 2000 into 3000, and you will basically give 6,000, that means 6 million or 60 lakhs. So, thus Indian Auto should produce 2000 mid-size cars. If Indian Auto has not yet been required to manufacture at least 1000 cars of each type. Oh, remember, so here the constraint was that each car has to be of 1000 variety or more. So, anything less than 1000 was not allowed. So, in that case, if it was not there, that restriction was not there, then the optimum solution would have been, that means any number can be produced for the cars, would have been 570 for compacts and 1715 for the mid-size cars. So, this is totally a different scenario, and output which you will get depend on the constraints which are changing. Next, we will consider the investment problem, and here is the problem which is being formulated. Jagdish Investment Company Limited is considering 4 investments. So, they want to invest in different investments. Investment number 1 will yield a net present value or NPV of rupees 16,000. Investment 2 will give a net present value of 22,000. Investment 3 a net present value of 12,000, and investment 4 a net present value of 8,000. So, each investment requires a certain cash outflows at the present time. So, you want to basically utilize that money. So, investment number 1, number 2, number 3 and number 4, the values are 5,000, 7,000, 4,000 and 3,000. Currently 14,000, these are all the values I am talking about are all in Indian rupees. So, 14,000 available for investment to that company. Formulate an integer programming whose solution will tell Jagdish Investment and Company how to maximize the net present obtained from the the investment what Jagdish company is making in the investments 1 to 4. So, as in linear formulation we need to define. So, define either invest, not invest, quantum of investment which is required, so on and so forth. So, as in linear programming formulation, we begin by defining a variable for each decision that Jagdish Investment Company must make. So, this leads us to define a 0 1 variable, decision variables. So, which is what? X 1 you will invest in investment 1, x 1 is if it is 1, x 1 it is 0, that means you would not invest in decision 1. Similarly, x 2 1 0, x 3 1 0, x 4 1 0 would mean that you are investing in second option or second investment, you are investing in third investment, you are investing in fourth investment. So, all of them are 1, actually it would mean that you are investing in all of the 4. If all of them are 0, it will mean that you are not investing in any of the investments for Jagdish company. So, for example, it states that if x 2 is 1 and if investment 2 is made, and if x 2 is 0 if investment 2 is not made. Now comes the net present value. So, net present value obtained by Jagdish Investment Company is like follows. So, if you have read the problem, so it gives the net present value for investment 1 is 16,000, 2 is 22,000, 3 is 12,000 and the fourth one is 8,000. So, the values would be corresponding 16 into x 1. So, let me so it will be 16 into x 1 depending on if it is 1 you will basically get 16,000, if it is no investment it will get 0 because 16,000 into x 1 when x 1 is 0 will yield a value of 0. Similarly, the net present value for the second one will be 22 into x 2. Similarly, for the third one is 12 into x 3 and the last one is 8 into x 4. So, all these 1000 values are omitting from mentioning. So, hence the investment is given. Now, you have to check the constraint also. So, I will come to the constraint later on. So, considering the time for this 40-second lecture is already over, I will stop here and discuss the problem in more details in the next class, which is the 43rd class. Have a nice day and thank you very much.